Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this series of lecture on elements of solar energy conversion. So, we have done 13 lectures so far and this is the lecture number 14. Okay, so what we have covered so far, like any other class, we will just mention them so that we know where we are, but we will mention them in short notations, not going into detail. So, first we covered basic concepts, then prediction of solar radiation. Third thing we covered the correlations between major angles, okay, that we derived, and then we have looked at shading, how it affects the solar energy conversion systems, and then we have started looking at the estimation of solar radiation on a tilted plane. So, in the last class we have covered about half of it and today we are going to finish that part. Okay. So, today we will continue with topic number 5 as mentioned here. Okay. So, that is the plan, and if we have enough time left we will go to the next topic, which will be looking at the solar collectors. Okay. So, that is the interesting part where you will actually see how these collectors work and all, but before that we have to build up the background that this collector study requires. Horizontal plane value to the tilted plane value, and then we had few component of the diffuse radiation. First one was the isotropic sky, and we have introduced the view factor which connects from the collector to the sky, that FCS, plus the next diffuse component was termed as circumsolar, which is designated with the subscript CS, and again we introduced or we used this conversion factor which takes from the horizontal value to the tilted plane value. Okay. That is the circumsolar part, and the next part was the horizon brightening part, right. So, IDHZ, which is horizon brightening diffuse radiation, and the view factor was from the collector to the horizon area, okay, plus I into rho g into FCG. This last term, it represents the reflected part, where I is the reflected part from the ground, the horizontal plane around it, and I here stands for the horizontal plane value of the total radiation, and rho g is the reflectivity, the average reflectivity of the ground plane, and the corresponding view factor, which is FCG. So, this is where we stopped in the last class. So, I again want to emphasize that this I without any subscript, this is for the horizontal plane total radiation. Okay. This IT, that is on the tilted plane, right. This IB stands for the beam radiation, and whenever you have a subscript small d, that means it is diffuse. Okay. So, just to remind you, now the next step would be to actually find out these values. Okay. So, we have formulated what would be the form of the equation, what would be the major terms, okay, that is coming from the concepts. Now, what we need to do? We need to put values corresponding to these different these symbols, right, and for that we need to make some assumptions. Okay. So, let us first take a simplified model which often serves the purpose completely. So, we do not need any further complications to be introduced. So, simplified model, what it does? It does not differentiate between the isotropic diffusion diffuse radiation, the circumsolar diffuse radiation, or the horizon brightening diffuse radiation. Okay. What it does? It takes only the isotropic sky. So, the simplified model we call isotropic sky model, which is actually the most widely used model, most widely used because of its simplicity. Okay. And it does not call for any more complication until and unless we require for or we thrive for further accuracy. So, if we get reasonable accuracy for our purpose, then we stick to such simplified model with isotropic sky. Okay. So, if we take the isotropic sky only, what will we get? So, isotropic sky assumption, it tells that no circumsolar diffuse radiation as well as no horizon brightening diffuse radiation. Okay. So, what we are left with? So, let us say that then what we are left with. Okay. So, if we have, this is the point where we have the collector and we have a tilted plane. Suppose this is the plane that we are interested in looking at the radiation intensity. Okay. So, what does a sky dome look like? So, sky dome will look like this, right, and so this is the sky dome, and this angle the collector makes, this angle is the tilt angle beta, right. So, you can see that the plane, it sees portion of the sky dome, right. So, this portion of the sky dome the collector sees behind the collector, the portion is not visible to the collector. Visible, what do you mean by that? The collector does not have a eye, but visible means that the radiation can directly reach to that collector from this blue colored portion only. Okay. So, this is visible, and I am putting some inverted commas, so that you know what the visible means. Visible portion of the sky dome. Okay. And what else does this particular collector sees? It sees the portion of the ground, right. So, let us say this is the portion of ground that the sky dome sees. Okay. So, this is the portion of ground that the tilted plane can see. Again, see means from where the radiations can directly reach on the surface of the collector. Okay. And this beta is the tilt angle. Okay. So, if this is the case, and under the isotropic sky assumption, what we are assuming, that this whole portion is, this blue portion is isotropic. It has certain intensity which is coming equally from all parts of the dome. So, first we need the view factors. Okay. View factors are from the collector to the sky, and the other view factor is from the collector to the ground, right. So, what would be these view factors? And now we are not going to calculate these view factors or find out, which is a geometric concept which you have learned how to do it in case of radiation heat transfer. So, what we will do, we will just state what these view factors will be. So, this collector to sky view factor will be 1 plus cos of beta divided by 2. Okay. So, I insist that please check this expression, whether it is true or not. From the consideration of geometry, please check this expression, and here beta is the tilt angle. Okay. So, that is the view factor from the collector to the sky, and from the collector to the ground is 1 minus cos beta over 2. Okay. Very simple expression, but you can check that again, please check. Okay. Now, note here that these two view factors add up to 1, right, and that is what they should do. From the view factor algebra, you know all the surfaces that is visible from a particular surface, the view factors will add up to unity, right. So, that is why here also we see that. So, this is kind of expected, but it is good to verify that this is true. Now, if these are the view factors, the expression that we have written, which will be simplified in terms of the isotropic sky, as well as we will put these view factors into the expression, and what will we get? We get this particular expression where the beam part is unaffected because we did not make any changes to that, and the diffuse part, now we have gotten rid of all the different diffuse parts like isotropic, circumsolar or the horizon brightening part, we can only write ID, which will tell you the isotropic sky diffusion intensity, and that is a single value, and the view factor is 1 plus cos beta divided by 2. Okay. So, that is the total diffuse radiation coming from the sky dome plus the ground reflected part, where we will use the view factor with the ground. Okay. So, this is the expression that we get under isotropic sky. So, here you note that single diffuse radiation term, and hence no further subscript such as your circumsolar or horizon brightening or isotropic etc. are used. No further subscript is used. Okay. Only ID will tell you that that is the all diffuse radiation that we have. Okay. And this is the last term is the ground reflected part. Now, that is the simplest model. Okay. Simplest model. Now, if we want to introduce little more complexity to that, so next important complexity to introduce, next level of complexity is introduced through the circumsolar part. Okay. And circumsolar part, we know that it is related to the beam radiation direction, and we use the same factor RB, which is used for the beam radiation part. Okay. So, now we will look at anisotropic sky model. Okay. Anisotropic sky means it is not uniform throughout the sky, it has a background thing which is isotropic, and then for the circumsolar part or where the sun lies, around that we have certain enhanced intensity which we will include in the circumsolar part. Okay. So, what we do, we distribute the total diffuse radiation in two parts. So, IDT, T stands for the tilted surface and ID stands for the total diffuse radiation, that is IDT isotropic plus IDT circumsolar. Okay. So, here the horizon brightening is still neglected, we did not introduce that. Okay. So, if we have these two parts, then we need to have some distributing factor, how we are going to distribute between isotropic and the circumsolar, and for that we introduce this anisotropy index. Okay. An anisotropic index is designated as AI, you can see anisotropic, and that is why AI, and AI is defined to be IBN divided by ION. what is that? So, and okay, first the most basic thing, that ION is our extraterrestrial normal radiation intensity, right. O means outside the atmosphere, that means the extraterrestrial value, and it does not depend on whatever be the atmospheric condition, whatever be the weather condition, cloud is there or not, it does not depend on that. So, that is why we base our anisotropy index in terms of ION. And what is in the numerator? It is the intensity, and again I should say normal intensity of the beam radiation on the surface of the earth. Okay. Whenever we do not have the index or subscript O, that means we are measuring it on the surface of the earth, not outside the atmosphere, surface of the earth. Okay. So, here you can see that what does this anisotropy index tries to capture. It captures how much of the extraterrestrial radiation is available in terms of beam radiation. So, it is kind of tells you that let us look at two limits. So, first one is a complete lack of beam radiation. That means all the radiation that is available is in the diffuse form, okay, all in diffuse form. So, there you can see that whether basically it means it is a completely cloudy day, you cannot see the sun, then how can you have anything specially bright portion around the sun. So, circumsolar part will be completely absent, right. So, this means that when AI is 0, then the circumsolar part will be absent, right. That is intuitively makes sense, right. And the second limit that you can see when everything that is available is in the beam form. Okay. So, everything in beam form or beam radiation, that means a clear sky condition, right. And in that case AI will be 1 and the circumsolar part will be maximum. Do not you agree? So, these two limits tell us that okay, the anisotropy index gives you certain distribution when the circumsolar part will be higher or lower, that is what we are trying to catch through this anisotropy index. Now, if we introduce this anisotropy index, then we can write this total diffuse radiation on the tilted plane will be equal to two parts. One will be circumsolar part, right. This is the circumsolar part, which you can see that it has this signature RB, which stands for the factor which is related to the beam radiation, right, and it also has this anisotropy index, okay, and this ID is the total diffuse radiation. Okay. So, ID is total diffuse radiation. So, it tells us the factor which will be circumsolar, in which includes the anisotropy index as well as which includes the RB, the beam factor. Okay. And the second portion is the isotropic part, which will be where we have this factor 1 minus AI, that tells that 1 minus AI is the other than what you have other than the circumsolar part. Okay. And we have of course have this view factor, okay, view factor for the sky. So, this gives you the isotropic contribution to the total diffuse radiation. Is that clear? So, we have now introduced little more complexity, and we have now divided the diffuse radiation part into two parts. One is isotropic contribution, the other one is circumsolar contribution, and to find out that distribution, we have introduced one parameter which is called anisotropy index, and it depends on the cloudiness or the aerosol content of the atmosphere, or rather the condition of atmosphere dictates what the anisotropy index will be. Okay. So, under this anisotropic condition or anisotropic sky model, what we finally get, the total radiation to be IT will be equal to IB plus ID into AI, and we can club them together, the beam part as well as the circumsolar diffuse part, in one term, and where both of those terms include RB plus the isotropic part of the sky radiation 1 plus cos beta over 2, okay, plus the ground reflected part which stays as is. Okay. So, this is the beam plus circumsolar diffuse, okay. This is the isotropic diffuse part, okay, and the last term is the ground reflected. And again it is diffuse radiation, as we are assuming that the ground is not a specular reflector, but a diffuse reflector. Okay. So, again this is diffuse radiation. Okay. So, that is what the anisotropic sky model gives us. Now, last bit of complexity that we so far did not consider is the horizon brightening part. So, let us include that one as well. So, if we include horizon brightening, what changes? The model will do. Okay. So, what we do? We include it in the form of a correction factor. Okay. We do not include it absolutely independently, or we do not include it in the form of a separate term, but we include it as a correction to the diffuse radiation that we are already taking. And this correction factor we introduce is 1 plus f multiplied by sin cube beta by 2, okay, or sin beta by 2 cubed. So, you can see that this correction factor depends on the beta or the tilt angle. Okay. Tilt angle will tell you how much the horizon brightening will be effective, because if you have a horizontal surface, it will see very small portion of the horizon, but if you have a tilted surface, then it will see one portion of the horizon very directly, right. So, that is why the tilt factor dependence is there. So, please note this. Okay. And the other thing that we see here, which is not so far introduced, is a factor f. Okay. And what this factor f? F is found by this quantity I b divided by I and square root of that. Now, how this is derived and validated? For this you have to look at the proper or the appropriate reference papers, and the derivation of these are of course beyond the scope of this course. Okay. So, but you note the physical significance of this, because this tells us I b is your beam radiation intensity on the horizontal plane, and of course, whenever there is no O, we have on the surface of the earth. Okay. And I is what? I is the total radiation intensity on the horizontal plane. So, again it is a relation or a ratio between the beam radiation and the total radiation. Okay. So, and the square root of that gives you the correction factor. Now, if we include that correction factor in our expression, then if the horizon brightening part is included in the anisotropic model, then the final expression that we get is the total radiation on the tilted surface, that is I b I d a I multiplied by R b, just like the previous expression that we had. Then I d 1 minus a I, this is the isotropic term we are writing. Up to this we have seen earlier, right. Now, for the horizon brightening, what we are doing? We are multiplying this whole thing by the correction factor. Okay. So, you can see here, okay, let me just finish it first, plus I rho g 1 minus cos beta divided by 2. Okay. So, these two terms, the first and third terms, they are exactly the same, only difference we have is here, right, in the second term, where what difference we have, this 1 is giving you the isotropic sky part, sky contribution, okay, and the other one, this part is giving you the horizon brightening portion. Okay. So, basically we have not written it in separate form, but we corrected the anisotropic or the isotropic sky term for the diffuse radiation with this factor, which includes the effect of horizon brightening. Okay. So, this is the most general form of tilted plane intensity estimation, okay, which includes everything. But again I should stress here that such complicated model is not often used, rather we use the simple isotropic sky model, which does not include the circumsolar or horizon brightening portions, and even then we are very close to the actual estimation. So, let us go to the next topic, which is related to, of course, this particular tilted plane radiation intensity estimation, and that we call the radiation augmentation. Augmentation means what? To enhance, to increase, right, to add to the radiation that we have. Now, whenever we want to add something, we need to put some extra effort, right. So, if you just place the collector at certain location at certain tilt angle, then whatever is available you will get. Now, if you want to add this, what we do? We place certain kind of reflectors in proper positions, so that the intensity on the collector increases. That is what is called radiation augmentation. So, suppose we have a collector here. Okay, inclined to certain angle beta with the horizontal. So, if this is our collector, we can increase its radiation on it by placing a augmenter. Okay. This is what? This is nothing but a reflector. So, even if you do not have it, the ground under it will reflect some portion of the radiation to the collector, but the ground reflectivity is much lower, right. So, if you place a reflector which has higher reflectivity, so what we will have? You will have certain radiation that is coming here, that will be reflected to the collector, and that is how we are augmenting. Augmentation through increased reflection from the reflector. Okay. Now, why are we saying that the reflector is placed on the ground? we can place it somewhere else, so that the reflection increases, right. But in that case we are going to block certain portion of diffuse or beam radiation as well, right. So, if we place that reflector on the ground, the other portions of the radiation that is reaching on the collector is not going to be affected. Only thing, we are increasing the ground reflectivity to increase the total radiation. Okay. So, that is the idea of augmentation, and for that how to quantify such augmentation. Okay. So, for that we need to find out how much of this reflected radiation from the reflector will actually reach the collector, right. That will be the added part to this reflection or to this total radiation, right. So, for that we need to quantify this view factor between these two. So, let us now take some dimension, so that we can find out the view factor. So, this is the collector, this is the reflector, okay. And let us say yeah. So, this is collector, we will designate it with C, and this is reflector, we designate that with R, and the dimensions here, this is, we say this is N, okay. This is P, okay, and this particular dimension is M, and let us say this angle. So, of course, if reflector is on the horizontal plane on the ground, this will be your vertical direction, okay, and the angle between these two, let us say this is psi, okay. So, if this is the dimension, then so under the isotropic sky model, which is the simplest one, what we have seen, that IT can be written as IBRB plus IDFCS, which is the view factor from the collector to the the sky, plus IR rho r, this is from the reflector, right, plus I rho g f c g. Okay. So, basically what we are seeing here, that the ground reflected portion is now broken into two parts. So, one is, so this is ground reflected portion, now has two parts. One is from the reflector, right, and the second one is from the rest of the ground, right. So, now the whole ground is not in the same reflectivity or same condition. So, what we do, the rest of the ground is separately dealt with and the reflector is separately dealt with. Okay. And here you see that IR here is the, this IR is intensity on the reflector plane, okay, that you have to estimate first, right. Now, here we can write that the view factor algebra tells us that FCS, so from collector to the sky, plus FCR, which is collector to the reflector, plus FCG, that is collector to the ground, all three must add up to 1, right. So, that is what the view factor algebra tells us, and FCS we have already mentioned in earlier portion of this lecture. What we wrote? This is 1 plus cos beta divided by 2, right. But what about this CR and FCG? FCG and CR we do not know, right. So, either of them we have to know. If we know one, then the other will be obtained from this summation rule, okay, because among 3 terms we know 2, the third one we can get. Now, how to? So, let us try to find out how this we can find this FCR, okay. AC into FCR will be equal to AR into FRC, right. That is the reciprocity rule for the view factors. Now, if we are after FCR can be obtained if we know FRC, right, because areas are anyway known. So, let us try to find this FRC. So, this FRC can be charted as a function of these different parameters, right, N, P, M and psi. Okay, these 4 parameters will tell us what would be the value of FRC, and that can be obtained I mean purely from geometry. Okay. So, what we can do, what is usually done is that this NP, so we plot isolines for different P by M ratio as a function of different N by M ratio and for certain psi. Okay. So, that way we take care of the all the 4 parameters that FRC depends on. So, let us look at such a chart. Okay. Here is such a chart where we are trying to find out this FRC, okay, the view factor from the reflector to the collector, and here we are plotting it for different N by M, and what we are plotting? We are plotting isolines for different P by M, okay, and everything we are doing for a certain psi. Okay. So, that is how we can plot for psi equal to 120 degree, psi equal to 150 degree and all. Okay. So, that way we plot this FRC, and if you have something, some particular variables which fall in between, as you know that you have to interpolate, right. So, if something happens to be here, like here. So, you have to interpolate between these two lines and then you will get a particular value, okay, for FRC. So, that is how this FRC is found, and once this FRC is found, the other things are easily found out. Okay. So, once this FRC is found, then FRC is found, and then we can find this FCR, okay, from the reciprocity rule, and from there when FCR is known, rather when this FCR known, FCS is already known, that is 1 plus cos beta by 2, and then we can find the FCG. So, that tells us all the required view factors, and we can place them in the expression of IT, and we can obtain the value or the augmentation that happens due to the reflector. So, last thing that we are going to talk about today is a special case. A special case with reflector or radiation augmentation. So, why do we call it special case? Because often we see that rows of solar collectors are placed very long distance. Okay. So, if you look from side view, it will be somewhat like this. So, suppose these are the solar panels which are placed perpendicular to the plane of the board, and you have a reflector associated with it. Okay. So, this is the collector plane and this is the reflector plane. Okay. And we can assume that the end effects are negligible, because it is almost a two dimensional case when you have one dimension very long, and that is how its effect is negligible. So, what we have here also, we can take this to be of length n and this to be of length p. Okay. And if we assume or if we write this length, we can write it to be S. Okay. So, this angle as earlier we will designate with psi. So, this is exactly same as the earlier case, but here the m thing is absent, and we are assuming that this is infinitely long perpendicular to the direction of the board. Okay. So, here what we get is that we will use Hotel's crossed string method. If you are not familiar with this, please go back to the radiation heat transfer book and look at this particular method. Then you will find that this FRC can be obtained in terms of this NP as a function of NP and S. Okay. Now, first we have to find what that S will be, because that will depend on NP as well as the psi. So, S will be, this is a pure geometry problem, you can find this out by yourself. So, S will be n square plus p square minus 2 n p cos psi whole to the power half, that means square root. And when we have S, then FRC will be nothing but n plus p minus S divided by 2p. Okay. So, that is how you get for a long panel of solar collector with radiation augmenter, we will have FRC little simplified than looking at the chart, that will be n plus p minus S divided by 2p. Okay. So, this is the simplification for a two dimensional long array of collector. Okay. So, here we stop for today, and in the next class we will start with flat plate collectors, which is the most basic form of solar collectors. So far we have covered all the basics that are needed for your solar energy conversion. Now we are going to see from the next class, we will actually see the conversion devices. Thank you very much for your attention.